Welcome to Carrier Software Systems. It is our pleasure to bring you this training session on modeling VRF systems and HAP software. Let's start with our first objective, which is to configure a VRF system in HAP for loads. To define a VRF system in HAP, the user must first create a new air system. We will use a VRF system already created for this training session to make our configuration go faster. The VRF system is a complete air system, so it is defined at the air system level, not at the plant level. The plant level in HAP is for hydronic equipment applications like boilers and chillers. On the General tab, after you give it a title, specify equipment type as terminal units and air system type as variable refrigerant flow. Notice the other choices of popular terminal type systems in HAP like water source heat pump, geothermal heat pumps, 2 and 4 pipe fan coils, induction beams, chill beams, all kinds of popular systems. It is important to understand when to use the terminal units equipment type. Whenever your HVAC system is comprised of lots of fan coils or terminals, as we have been calling them, throughout the building, this is the air system that you want to use. All of the terminals can be quickly rolled up into this single air system model. A 10-zone office system will be used for our VRF example. First, you must determine if the ventilation air is being handled by each VRF terminal directly or not. If using direct ventilation, this means each VRF terminal will have to be sized to handle the ventilation load in addition to its peak zone load. A separate dedicated outdoor air system, or DOAS, is very common, however, especially on larger projects, so we will make that selection. The DOAS can be sized to handle the exact ventilation load, or some of it, or all of it, plus some of the zone and space loads. It depends on the discharge temperature you specified for cooling and heating coils. When you use a DOAS ventilation system, the DOAS Components tab will become enabled. If using direct ventilation, this tab is disabled. We will use a DOAS in our example. Under the DOAS Components tab, we can define the inputs for our DOAS. We will configure the ventilation air airflow control as constant. That's an ASHRAE compliant methodology, as is demand control ventilation. We will use constant for our project. Since ASHRAE 2013 was selected back at the start of this example under Preferences, that's what shows up here now. By the way, there's a separate training session already done called Setting User Preferences that goes through this topic in detail. By choosing ASHRAE here at the system level, as opposed to some of the spaces, the software will incorporate all of the ASHRAE corrections required for compliance with Standard 62.1. Next, under Ventilation Reclaim, we will configure a 55% efficient, sensible, and latent ERV, Energy Recovery Ventilator. Like a desiccant wheel, for example. There is a 500 watt motor turning the wheel, so we will configure that as 0.5 kW. This will be picked up as part of our energy analysis. Energy standards require the use of ventilation recovery on air systems that are 100% outdoor air. Under Cooling Coil, we will configure a DX air-cooled unit with a final set point on the unit discharge air of 75 degrees. A DOAS unit is traditionally controlled by discharge air sensors, not by zone thermostats in the spaces. If we want the DOAS to be sized for the ventilation load exactly, then we will ask for neutral conditions of 75 cooling and what will be 70 degrees heating, which corresponds to the thermostat set points in the spaces for this project. So under Heating Coil, we will use a combustion natural gas heat exchanger of 81% efficiency, and that will be put in back at the Equipment tab, and we will say that we have a 70-degree discharge set point. We could equip this DOAS with humidification or dehumidification. That's a reheat coil, but we'll go right on to the vent fan, and we'll say that it has a total static pressure of about 3 inches. We don't know the brake horsepower or kW yet. We'll go back later and put that in after we make a selection perhaps, and get this load and energy even a little closer than guesstimating the total static. And we'll configure it with a forward curve fan. Under duct system, we will say we do not have a drop ceiling with the space above acting as a return air plenum, so we will select the choice which is a ducted return. If you need to know more on this return air plenum topic, or any topic, you can put your cursor there and hit the F1 key, and you will go to the help system in HAP that will give you all the information you need to know about that input. We'll go back and say we have a ducted return. Continuing on under exhaust fan, we will say we have a forward curve fan at 1.5 inches total static pressure, again to pick up some preliminary fan heat and energy consumption. This is the fan that delivers the return air back to the ERV to serve as the source airflow to pre-cool and preheat the incoming ventilation airstream. This completes the DOAS Components tab. Let's go to the Zone Components tab next. Under the Zone Components tab, assign each space to the appropriate zone from 1 to 10. We've already done that to save us some time. In the traditional tabular air system input like we're doing, the spaces are assigned to zones as shown here. If we were using the equipment wizard, however, we could assign these spaces by dragging and dropping them quickly with our mouse. We will set the inputs for thermostats, common data, and terminal units as shown here. Under thermostats, we'll have set points identical for all zones, even though we can uncheck this and put in separate thermostat day and night set points. We will leave a throttling range of 1.5 degrees in there. You can F1 that and read all about what throttling range is. And we will use a fan thermostat schedule which starts and stops the day set points. And if we wanted to take a look at that thermostat schedule that we're using, to run loads, we're saying that it starts at 5 in the morning and goes to later in the evening with the occupied cycle. Under common data, it lets us put in the cooling coil supply air temperature. For cassette type VRF terminals, maybe it's more in the 57-58 degree temperature range versus something like, let's say, chilled water down in the mid-50s or lower. And this is the temperature coming out of the diffuser into the conditioned space. For heating, we'll say, because it's reverse cycle heat pump, when we have heating, of about 105 degrees. And this will be used in CFM calculation. Under terminal units, we will say that we have the default of ceiling supply and ceiling return, which assigns a what's called ventilation effectiveness value based upon ASHRAE standard 62.1. We'll leave 0 as a minimum airflow. And now we have an opportunity to differentiate the VRF fan energy from other systems. Our example made use of cassette type indoor terminals, we'll pretend, with integral diffuser and no ductwork. That means we could put in a total static pressure that is relatively low to reflect the small fans in the cassette unit terminals. I've used a value of 0.20 TSP inches for our example. After you run the loads, HAP will display the resulting brake horsepower and kW generated by this TSP input, and that'll be in the zone sizing summary. Then you can make actual product selections, having sized it, and go back if you'd like and re-enter the actual watts or brake horsepower values of the product that you'd like to actually model. That's completely up to the user to be most accurate in that respect if you'd like to be. Entering known product data, by the way, is the most accurate method of modeling when it comes to VRF systems, or any systems for that matter. We will choose to leave the Sizing Data tab defaulted to Computer Generated so we can focus the remaining discussion on the unique inputs for VRF systems. Most of the VRF specific inputs reside under the Equipment tab, which is next. Under the Equipment tab, there are three major buttons in this particular project. These buttons define the cooling and heating efficiency and capacity of the DOAS unit and of the VRF outdoor units. The first two apply to the DOAS unit. We will cover them first. Under Edit Equipment Data button for equipment sizing, you can auto-size with or without a capacity oversize, or user-define the actual coil capacity. We will auto-size. Now you are given three choices for describing the efficiency of the DOAS cooling. You can input the known unit AHRI performance rating value in EER, or you can enter the actual compressor and outdoor fan kW, if you knew it. But unless you have already run the load, which we haven't, you can't put in the equipment data yet. Or you can have HAP automatically size the unit and access the ASHRAE 90.1 minimum equipment efficiency tables built right into the software. It'll use the version of 90.1 we specified at the preferences at the start of the project. This is the option we will use for our DOAS right now. Lastly, we set the low temperature cutoff to -10 degrees. This effectively says we will allow the compressor units to run on cooling duty, if required, when it is very cold outside. HAP will make the determination each hour if and when the compressors need to run. We'll say OK and go to the DOAS Heating Unit tab. Under the DOAS Heating Unit, we will auto-size with an 82% efficient gas heat exchanger. We'll go ahead and put in a 10% oversize also. And say OK. The third button is the one with the vast majority of VRF specific inputs. VRF Outdoor Unit Edit Equipment Data. Let's click on that, and this opens up the equipment data screen shown here. Let's go through each one of these from top to bottom. Equipment sizing can be either user-defined or auto-sized. This input specifies whether the computer will automatically determine the capacities required for the outdoor units, or the user will directly specify the capacity for that unit to be modeled. For energy analysis, when you want to be very detailed in your design and you are modeling a specific brand or size of unit, choose user-defined capacity so you can directly enter the cooling and heating capacities. Of course, you don't know the capacity until you go ahead and auto-size and then go back in and change it to user-defined. That's typically the sequence of what will happen. With that in mind, in our example we are doing, we don't know the load yet to be able to use user-defined. So for now, let's leave it on auto-size. Go through all the remaining inputs under the Outdoor Unit Equipment Data tab that we're in now. Then we can switch and go back to this portion over to user-defined and make an actual VRF system selection outside of HAP. This user-defined data we will use for energy analysis and will be from a manufacturer's catalog or VRF selection program, but it will represent an actual rated system. So for running loads right now, we will auto-size. Design Outdoor Air Dry Bulb designates the standard outdoor air temperature at which a gross cooling capacity and gross heating capacity are defined, typically 95 cooling and 47 degrees Fahrenheit high temperature reverse cycle heating for heat pumps. So it defaults to that. Estimated maximum load. This is displayed by the software and is not user editable. If you haven't run the load yet, then this item will be blank. Well, we've run the load prior to me booting this up, and we see what our loads are. And there they are, 190 MBH and 55.4 MBH required for reverse cycle heating. Design capacity defines your gross cooling capacity of your VRF outdoor unit or units at the conditions we just discussed. This input is enabled only when you select user-defined capacity. This value is typically obtained from equipment selection software or product catalogs. Capacity oversizing factor defines the additional capacity added when using the auto size capacity option. Remember, you can auto size with no oversize if you'd like. Next, we have several choices to define the energy performance of the unit at the design point. Separate values are specified for cooling and heating. 3 options are provided for defining this important data. Option number 1, AHRI performance rating, allows you to enter a standard EER or SEER value for cooling and a standard COP or HSPF value for heating. During the energy simulation, if you take this option, HAP will automatically derive the compressor and outdoor fan kW from the EER formula for this rating to be maintained. It'll do that by subtracting the terminal indoor fan power value you had entered earlier. Outdoor unit input power. With this choice, you are required to input the sum of actual compressor and outdoor fan power for the outdoor VRF compressor units you will utilize once you run the load and make an equipment selection and you choose to model it this way. This is considered, however, like we mentioned, the most accurate choice of the 3 methods we are explaining. This input kW is used together with the design outdoor air temperature and gross capacity you entered to form what's called an anchor point for the built-in algorithms in the HAP software to then calculate application-specific hourly part load performance curves, taking into account all of the hourly variables shown here on this PowerPoint cell. Choice number 3 is to model VRF performance with an ASHRAE 90.1 minimum equipment efficiency. The program will automatically determine the equipment efficiency rating, compliant with ASHRAE, and no better and no worse, after it runs the load and goes into the applicable standard 90.1 lookup table, which would correspond with what we picked under preferences at the beginning of the project. In our case, it would be 2013. Let's go down to compressor type. The VRF performance model in HAP contains performance curves for the major types of VRF outdoor compression technologies on the market. Included are variable speed rotary, variable speed scroll, and digital scroll. Consult the manufacturer you are modeling for this input, for which of the 3 is applicable. We will pick variable speed rotary. Refrigerant piping physical length. Long line length is a unique characteristic of the VRF system, increasing its application and flexibility. It's one of the huge advantages of this system. Here you specify the equivalent or the measured length depending on which of the compression technologies you choose. The length is the one-way distance from the VRF outdoor unit to the most distant indoor unit. The long interconnecting lines between indoor and outdoor affect the cooling and heating loads and energy calculation. Refrigerant piping vertical distance means you should specify the greatest vertical distance of a terminal in the loop from the outdoor units. Specify a positive value if the outdoor unit is above the indoor unit, for example, roof mounting. Specify a negative value on vertical distance if the outdoor unit is below the indoor unit, for example, a ground level outdoor unit serving indoor units on upper floors. Heat pump cutoff outdoor air dry bulb. It's the outdoor air temperature below which the heat pump turns off and the equipment runs on 100% auxiliary electric. Many manufacturers don't turn it off when it gets very cold, at which point you could put in an artificially low temperature like -20 and that means that it'll keep the compressors running at probably a COP greater than 1 anyway. So many people might say, why go to electric heat here? I'll just keep the compressor running. Heat recovery used? Yes or no? Simple input, but a major decision. This specifies whether the system model in HAP that you would like to use will have heat recovery controls. Some engineers call this a 3-pipe system. The building must have a simultaneous heating and cooling requirement to take full advantage of the heat recovery option through the refrigerant loop. This is a very popular feature of VRF systems, especially in climates like in much of North America, where there is both a cooling and a heating requirement in a commercial building. Auxiliary heating is a display-only item which reminds you that the auxiliary, also called supplemental heating for VRF system model in HAP, is resistance heat. Auxiliary heating upper cutoff specifies the outdoor air dry bulb temperature above which the auxiliary heating will be locked out. As a general rule, VRF systems should be satisfying the heat loss on reverse cycle heat pump when it's at least somewhere about 40 degrees or above outside. If not, the general consensus is maybe it's not sized correctly. So we'll use 40 degrees here, which I believe is what LEED suggests you use. At this point, we have configured our 10-zone VRF system with DOAS with the initial data required to run the load. After reviewed the load inputs, we will go back and user-define a VRF system for energy modeling. Let's now do our second objective, which is interpret design load output reports. To run the load, let's right-click on the VRF air system and print view design results. Let's keep it simple. Let's ask to preview the system sizing summary and the zone sizing summary. The system sizing summary for any terminal system equipped with the DOAS is just the DOAS unit itself. And the reason we know it's the DOAS, it says it's the DOAS right here. And if you look at the supply CFM, it's equal to the outdoor CFM. The VRF indoor terminals will be sized at the zone sizing summary coming up next because they are zone level equipment. Important items on this report include the DOAS tonnage, 2 tons, entering cooling dry bulb and wet bulb, leaving dry and wet bulb, CFM of 1779, and the heating coil conditions entering and leaving. Scroll down to the zone sizing summary. The zone sizing summary contains the sizing criteria for all the VRF terminals themselves, since they are considered zone level equipment. Under the terminal unit sizing data, cooling, are all the zone-by-zone peak, total, and sensible loads along with the coil entering and leaving dry bulb and wet bulb. The CFM per square foot for each zone is shown also. The second table is the terminal unit sizing data with selection criteria for the heating coil, fan, and ventilation airflow for each of the terminals involved in this system. Next, and very importantly, is the VRF outdoor unit sizing data. This is important information in that HAP gives you the capacity so you can select the actual VRF system or systems required for this building. Notice the peak coincident VRF indoor unit load is calculated in both cooling MBH and tons. In our example, the long line length refrigerant piping losses have been represented also in tons of capacity. This adds to the total VRF cooling system tonnage required. In our case, 18.3 tons. The heat MBH loss at the zone level is shown here. Most likely the reverse cycle heating capacity of a VRF system far exceeds this number. The The ventilation air heat load has been picked up by the gas heat exchanger in the DOAS, which was sized separately. So what we're looking at here is just the VRF system values. The DOAS is separately sized on the first report. For this job, we might select a nominal 18-ton or 216,000 B2 per hour VRF system, which is slightly undersized, but not much, with heat recovery, and that seems to fit this project fairly closely. The actual cooling output, however, as we look at the literature, is 206,000 or 17.2 tons. So maybe we do jump to a one size larger. Let's now meet our last objective, to configure a VRF system for energy analysis. We will choose to use the actual values for ODU compressor and outdoor fan from the selection we just made from the product literature, and define them into HAP at the Equipment tab under VRF Outdoor Unit. So we can pull that down and actually enter the values that we want. So I switch from auto size to user-defined capacity to be able to put in the actual capacity of the unit that I want to model for energy analysis. It does 230 MBH design capacity for cooling and 232 at 47-degree reverse cycle heat pump high temperature for heating, at an 18.2 kW for cooling and an 18.6 kW for heating. And I could say OK, and now I have configured this VRF system for energy analysis. We have sized the system and also set it up for operating costs. We would place the VRF terminal air system at the building level and attach utility rates and any miscellaneous energy consumers and go ahead and run the operating cost. Before we end this training session, let's discuss some important final concepts and conclusions. First, the VRF model in HAP is highly developed. HAP calculates an application efficiency each hour as operating conditions and loads change. That's why it doesn't use, for instance, an IEER in its part load model. That's much too simplified. HAP offers three major input options for VRF equipment modeling. Number one, direct input of the design kW like we did for the example. This is the most accurate approach since it directly specifies the kW of the outdoor compressor units. Number two, input of the EER or COP. HAP will then calculate using the EER or COP rating to arrive at the input kW at design. This can be relatively accurate, but is not quite as good as directly inputting the kW like we did. And number three, input of the maximum ASHRAE 90.1 efficiency, and HAP will once again use this value to arrive at the input kW of the units. VRF systems are just one of the many air system types in HAP that can be modeled. We plan on future training sessions on how to model additional systems as shown here. This completes our training session on modeling VRF air systems for both design loads and energy use in HAP. Thank you.